The morning of September 14, 1944, Recklinghausen Airfield, 70 miles north of Berlin. Hauptmann Hans-Werner Lerche circles the unfamiliar fighter sitting on the hardstand, its yellow-painted undersides gleaming in the weak autumn sun. The American aircraft bears the designation T9+HK in crude black paint, alongside the Balkenkreuz and swastika that mark it as Luftwaffe property. For 2 years, intelligence reports have described this stubby, broad-winged fighter dominating Pacific skies with a kill ratio that defies belief. 19 Japanese aircraft were destroyed for every Hellcat lost. Now one sits before him, and the numbers make no sense. 15,000 pounds loaded weight, nearly double the mass of a Messerschmitt, yet somehow faster in level flight than a Focke-Wulf 190 at low altitude. Lerche's engineering training rebels against the contradiction. Heavy fighters sacrifice performance for payload. The Americans have apparently rewritten the rules. The captured Grumman represents everything German aviation doctrine considers wasteful: redundant systems, excessive weight, brute force engineering solutions. Yet, Allied pilots fly these machines with confidence that German aces reserve for perfectly tuned aircraft. Today, Lerche will discover whether American industrial philosophy has produced genuine capability or merely expensive mediocrity dressed in propaganda. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The tail number visible beneath hastily applied German markings reads Bureau number 41834. Intelligence files indicate this particular F6F belonged to Fighting Squadron 3 aboard USS Yorktown before sustaining damage over Truk Lagoon in April. The pilot ditched near a Japanese-held atoll, where Wehrmacht coastal observation units recovered the intact airframe. 3 months of careful transport through submarine and rail networks delivered the fighter to Recklinghausen's Technical Evaluation Center, the heart of Luftwaffe aircraft testing. Lerche examines the Hellcat with methodical precision honed through evaluating dozens of captured Allied types. The fuselage stretches 33 feet, dominated by the massive Pratt & Whitney R2800 double Wasp radial engine. The same power plant drives the Corsair that British pilots praise with reluctant admiration. 2,000 horsepower channeled through a Hamilton standard 3-blade propeller. German engines achieve comparable output only through exotic fuels and temperamental supercharger configurations. The Americans build reliability into their fundamental design. His fingers trace the wing's construction. 13 feet span, 330 square feet of lifting surface. The metal skin feels substantial, each rivet placed with precision that suggests factory workers enjoy electricity and heating rather than freezing in unprotected assembly halls. The control surfaces move with hydraulic smoothness that German fighters abandoned in favor of weight savings. Ailerons stretch nearly the wing's full span, promising roll performance that conflicts with every principle of heavy aircraft design. The cockpit sits high, offering visibility superior to the Messerschmitt's cramped greenhouse. The armor plate behind the seat weighs 96 kilograms alone. The Americans protect their pilots with metal tonnage that Luftwaffe designers consider wasted payload. Lerche counts the 50 caliber machine guns, 6 Brownings, 3 in each wing, converging at a point 400 meters ahead. Crude compared to German cannon, yet American pilots achieve devastating effectiveness through volume of fire. Each gun carries 400 rounds. Total ammunition load, 2,400 rounds, enough for sustained engagement that would empty German fighters' ammunition bays 3 times over. The instrument panel presents the familiar chaos of American cockpit design. Gauges scatter across the panel with apparent randomness that somehow achieves functional efficiency: manifold pressure, cylinder head temperature, oil pressure, fuel quantity, all calibrated in incomprehensible English units: pounds, inches, gallons. Systems designed for farm boys with 300 hours of training to operate from pitching carrier decks in combat. The gear requires no mental arithmetic, no careful pilot technique. Hydraulic actuators handle complexity that German pilots manage through continuous attention to mechanical systems. Electric fuel pumps eliminate the hand wobble procedure that Messerschmitt pilots memorize before solo flight. Automatic mixture control adjusts fuel-air ratio without pilot input. The Americans have automated every function that German doctrine considers essential pilot skill. Lerche climbs into the cockpit, carrying a clipboard of notes compiled from interrogations of captured American naval aviators. The seat adjusts with simple lever mechanisms. Rudder pedals telescope for different leg lengths. German fighters demand pilots fit the aircraft. American fighters fit the pilot. The harness buckles with straightforward geometry requiring no instruction manual. Safety features apparent in every design choice. His checklist begins with procedures decoded from studying captured flight manuals and pilot notes. Battery on. Fuel selector to main tanks. Mixture rich. Propeller control forward. Cowl flaps open. Magnetos to both. Primer pump engaged. The procedures feel foreign after years of German fighters' Spartan simplicity, yet each step follows logical sequence designed to prevent errors by fatigued pilots landing on dark carrier decks. Engine start demonstrates American approach to mechanical reliability. The Pratt & Whitney catches on the second blade rotation, settling into a rumbling idle that shakes the entire airframe with 18 cylinders firing in sequence. Oil pressure rises immediately to specified range. No temperamental warm-up period, no careful nursing of cold metal. The engine runs like farm machinery designed for abuse by untrained operators. Lerche advances throttle experimentally. Engine response comes instantly, power surging with direct relationship between throttle position and propeller thrust. No hesitation, no careful mixture adjustment required. The supercharger operates automatically, managing boost pressure without pilot attention. German fighters demand constant throttle management to prevent engine damage. The Hellcat tolerates pilot technique that would destroy a Daimler-Benz in minutes. Taxiing reveals the wide track landing gear configuration. The gear struts spread 8 feet apart, retracting backward into the wings. Ground handling feels stable, almost pedestrian compared to Messerschmitt's narrow stance that demands constant attention. The Hellcat rolls straight with minimal rudder input. Visibility remains excellent, the nose angle allowing clear view forward. German radial fighters require S-turns during taxi to see past the engine. American designers elevated the cockpit enough to eliminate that dangerous procedure. Brake response comes smoothly through toe pressure on the rudder pedals. Hydraulic systems, again demonstrating reliability through redundancy. Every control feels over-engineered, built for strength rather than minimum weight. Lerche completes pre-takeoff checks at the runway threshold. Controls free and correct. Trim tabs set neutral. Cowl flaps open. Mixture rich. Propeller full forward. Magnetos checked individually, each producing expected RPM drop that confirms proper function. Fuel pressure nominal. Oil temperature climbing toward operating range. The aircraft demands less pre-flight ritual than a Focke-Wulf. Systems designed to operate correctly with minimal pilot intervention. He advances the throttle to take off power. Manifold pressure climbs to 54 inches of mercury, far higher than German engines tolerate without destructive detonation. The Americans achieve this through fuel quality that Luftwaffe supply chains cannot match. 2,000 horsepower flows to the propeller with mechanical confidence. The Hellcat accelerates down Recklin's concrete runway with straightforward directness. No swing tendency requiring heavy rudder pressure. The wide landing gear and large vertical tail maintain directional stability without pilot correction. Rotation speed arrives at 95 knots. Lerche pulls back gently on the control column. The Hellcat lifts off with a solid, progressive response that inspires confidence. Gear retracts with hydraulic smoothness, tucking into the wings without manual cranking. The climb begins immediately. Nose attitude shallow compared to German fighters' steep ascents. American pilots apparently favor cruise climb technique that maintains forward speed rather than maximum climb angle. The aircraft settles into climb configuration at 160 miles per hour indicated. Vertical speed stabilizes at 3,200 feet per minute. Excellent performance for a 15,000-pound fighter. The Messerschmitt climbs faster, but only by sacrificing payload, range, and systems redundancy. Cockpit noise remains moderate. The engine's radial configuration places cylinders away from pilot position, unlike inline engines that channel vibration directly through the fuselage structure. American pilots fly long missions in relative comfort. German pilots endure hours of vibration and engine noise that induces fatigue, affecting combat performance. Leveling at 5,000 meters, Lersch begins evaluation of basic handling characteristics. The Hellcat flies with an honest, predictable response to control inputs. Stick forces feel heavier than German fighters, requiring deliberate pressure rather than fingertip control. Yet the weight provides stability that allows relaxed flight. The aircraft maintains trim without constant attention. German fighters demand continuous micro-corrections. The Hellcat flies itself while the pilot scans for threats. Speed builds in level flight to 350 miles per hour indicated. Manifold pressure holds steady at military power settings. The engine runs with mechanical smoothness that suggests minimal wear despite combat history. American maintenance apparently produces power plants capable of sustained operation at rated power. German engines require careful management to avoid failures that ground entire squadrons. Lersch initiates a clearing turn to port. The Hellcat rolls into the bank with a firm, progressive response. Aileron forces remain reasonable throughout the maneuver. The turn develops smoothly at 60 degrees bank angle. No adverse yaw requiring heavy rudder pressure. The Americans designed their ailerons with differential geometry that minimizes crosswind effects. German fighters require coordinated rudder input for clean turns. The Hellcat rolls back to wings level with the same predictable response. No tendency to overroll or require back pressure. The flight controls feel harmonized, designed for pilot comfort rather than ultimate performance, a philosophy that produces competent pilots rather than demanding exceptional ones. Now the critical test. Lersch rolls the Hellcat hard to starboard, applying full aileron deflection. The aircraft snaps into a roll with startling rapidity. The horizon rotates with speed that contradicts the fighter's bulk. One complete revolution in approximately 4 seconds at 250 miles per hour. The second roll follows immediately, demonstrating sustained roll capability. 3 rolls total before Lersch neutralizes controls. The performance data crystallizes with undeniable clarity. The American fighter rolls faster than a Focke-Wulf 190 at the same airspeed. Impossible. Heavy fighters sacrifice roll rate for structural strength, yet here flies a naval fighter, built to withstand carrier operations, rolling with agility that exceeds Germany's Premier Interceptor. The full-span ailerons generate control authority that overwhelms mass penalties. American engineers solved the roll rate problem through brute force application of control surface area. The solution works despite violating theoretical efficiency. Lersch accelerates to 400 miles per hour in a shallow dive. He initiates another roll sequence. The Hellcat responds with slightly reduced rate but maintains impressive control authority. Where the Focke-Wulf's roll rate deteriorates rapidly above 300 miles per hour, the Hellcat sustains capability throughout its speed envelope. The ailerons remain effective even as airspeed approaches maximum permitted velocity. American designers optimized control surface design for high-speed combat rather than low-speed dogfighting. Vertical maneuvers demonstrate adequate but unexceptional capability. The Hellcat climbs at 45 degrees nose-up attitude, bleeding airspeed steadily until the stall warning buffet begins around 120 miles per hour. Recovery comes with simple forward stick pressure. No snap roll tendency, no wing drop requiring quick reflexes. The aircraft warns the pilot clearly before departing controlled flight. German fighters reward expert technique with superior performance. American fighters forgive mediocre technique with benign handling. The stall itself develops with gradual buffeting that grows in intensity. Control authority remains sufficient to maintain wings level attitude. Forward stick pressure breaks the stall cleanly without altitude loss beyond 100 or 200 feet. The entire procedure feels designed for novice pilots to execute safely. No opportunity for surprise departure into spin, no demand for precise recovery techniques. The Americans built an aircraft that young ensigns can fly from heaving carrier decks at night. That design, philosophy shapes every handling characteristic. Loop entry demonstrates adequate nose authority. The Hellcat pulls 4 Gs comfortably, climbing vertically, before arcing over the top. Energy retention feels mediocre compared to Focke-Wulf. The heavy fighter bleeds airspeed quickly in sustained vertical maneuvering. Yet recovery comes cleanly with ample airspeed remaining. American pilots apparently avoid prolonged vertical combat in favor of slashing attacks using speed advantage. Lerche extends combat flaps at 200 miles per hour. The aircraft's turning performance improves noticeably. Turn radius tightens at the cost of increased buffeting and drag. The flaps provide tactical flexibility without catastrophic handling degradation. German fighters often feature flaps intended primarily for landing. American designers integrate combat flaps into tactical doctrine. The Hellcat's turning capability at high speed proves respectable if unspectacular. Sustained turn radius at 300 miles per hour competes with Messerschmitt, but falls short of Spitfire. Yet the American fighter maintains energy better in rolling maneuvers that mix horizontal and vertical axes. Dive performance demonstrates impressive qualities. Lerche pushes over into a 45-degree dive, allowing airspeed to build past 450 miles per hour. The Hellcat remains stable, controllable, without buffeting or tendency toward compressibility effects. The controls stiffen progressively but maintain authority. Recovery requires significant stick force but develops smoothly without overstress. The Americans apparently built strength into the airframe that allows aggressive dive tactics without structural concern. Fuel consumption deserves attention. After 40 minutes of aggressive maneuvering, the gauges indicate internal tanks retain over half capacity. The Hellcat carries 237 gallons internally, plus capacity for external tanks. Range figures suggest combat, radius exceeding 600 nautical miles. The Messerschmitt carries barely 100 gallons, limiting its radius to 300 nautical miles. American fighters operate from carriers positioned hundreds of miles from targets. German fighters defend homeland territory from bases adjacent to combat zones. The strategic situations dictate utterly different design priorities. Gunnery platform stability impresses throughout the evaluation. The heavy airframe absorbs firing recoil that would disturb lightweight fighters. The cockpit position and control harmony allow precise tracking during deflection shots. 6 machine guns converge at harmonization point, creating a cone of fire that tolerates aiming errors. German fighters mount cannons that demand precise marksmanship. American fighters volume of fire that rewards approximate aim. Lerche returns to traffic pattern altitude, contemplating implications of the morning's flight. The Grumman Hellcat represents industrial philosophy fundamentally different from Luftwaffe doctrine. German fighters optimize individual performance through minimizing weight and maximizing specific power. American fighters optimize operational effectiveness through reliability, maintainability, and doctrinal flexibility. The approaches reflect competing assumptions about warfare's nature. Germany builds weapons for elite pilots, operating from established bases with comprehensive maintenance infrastructure. America builds weapons for average pilots, operating from mobile naval bases with limited maintenance capability. The Hellcat sacrifices theoretical efficiency for practical capability. Approach configuration follows straightforward procedure. Gear down, locked green lights. Flaps to landing position. Mixture rich, propeller forward. The aircraft slows to 130 miles per hour on final approach. Sight picture remains excellent throughout descent. The wide gear stance promises stable touchdown. The Hellcat settles onto Recklin's runway with barely perceptible impact. The robust landing gear absorbs carrier landing energy despite gentle contact with concrete. Brakes provide smooth, progressive deceleration. The entire landing sequence feels designed for pilots executing night approaches to moving decks in rough seas. German fighters demand precise technique for safe landing. American fighters tolerate technique variations that would destroy Messerschmitts. Lerche taxis back to the hangar area where engineers await his assessment. The technical evaluation will require weeks of detailed performance measurement, systems analysis, and comparative flight testing. Yet, initial impressions form conclusions that will shape the official report. The Hellcat embodies American industrial supremacy through engineering approaches that German doctrine considers wasteful. Yet the results achieve combat effectiveness that statistics cannot dismiss. 19-to-1 kill ratio. 5,000 enemy aircraft destroyed. Operational success that overwhelms theoretical objections. The captured fighter sits quietly on the hardstand, yellow undersides marking it as test aircraft rather than frontline threat, yet the implications extend beyond individual performance. American industry produces these fighters by thousands. Grumman factories roll Hellcats off assembly lines at rates exceeding Germany's total fighter production. Each aircraft carries redundant systems, reliable power plants, and comprehensive pilot protection. The industrial capacity to waste weight on safety features demonstrates resource abundance that Germany cannot match. Lersch completes shutdown procedures, engine winding down to silence. His logbook will record the flight with clinical precision. Time aloft, 1 hour, 15 minutes. Performance evaluation, comprehensive. Tactical assessment, disquieting. The American fighter does not excel in any single category, yet combined, capabilities produce weapon systems optimized for sustained naval combat operations. German fighters achieve superior climb rate, better high-altitude performance, and more potent armament, yet operational availability favors reliability over peak capability. The morning's revelation centers on roll rate performance that exceeds Focke-Wulf despite overwhelming weight disadvantage. The Americans solved the problem through brute force aileron design that sacrifices elegance for effectiveness. Full-span control surfaces generate authority that overwhelms mass penalties through mechanical advantage. The solution works. That simple fact troubles Lersch more than technical details. German engineering seeks optimal solutions through careful analysis, minimizing compromises. American engineering seeks effective solutions through aggressive application of available resources. When industrial capacity permits, brute force works. Germany cannot afford the American approach to fighter design. Resource limitations demand optimization that sacrifices capability for efficiency. Yet, efficiency proves less important than absolute capability when industrial output determines victory. The Hellcat succeeds not despite its weight, but because American industry can afford to build heavy fighters that accomplish missions. German fighters achieve theoretical superiority that operational reality undermines through mechanical failures, limited range, inadequate production numbers. Recklin's engineers begin detailed examination of the captured Hellcat. Removing panels reveals construction quality that explains the aircraft's reputation for durability. Riveting maintains factory standards throughout. Wiring harnesses route with careful attention to preventing chafing. Hydraulic lines feature redundant fittings that continue functioning after battle damage. Every system demonstrates design philosophy, prioritizing continued operation over minimum weight. The engineering team will spend months documenting the Hellcat's construction techniques, analyzing material choices, and measuring performance across the operational envelope. Their reports will fill technical archives with data that reveals American industrial capabilities. Yet strategic implications matter more than technical specifications. The United States builds these fighters faster than combat can destroy them. German industry struggles to replace losses from attacks that industrial capacity cannot sustain. September afternoon shadows lengthen across Rechlin as Lersch completes preliminary flight report. His assessment will join intelligence files documenting Allied aviation capability. The conclusions seem almost inevitable after 3 years evaluating captured aircraft. American fighters reflect industrial philosophy that German resources cannot duplicate. Mass production of reliable weapon systems defeats specialized production of superior individual aircraft. Mathematics favors industrial capacity over engineering elegance. The Hellcat exemplifies this harsh reality, good enough in all categories, exceptional in none, yet produced in quantities that overwhelm tactical advantages through strategic abundance. German pilots face opponents whose aircraft forgive errors, whose systems function reliably, whose industrial replacement ensures numerical superiority. Individual pilot skill matters less when operational losses can be replaced within days. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The technical evaluation of Bureau No. 4, 1834, continued through late September 1944 as Recklin's engineering staff conducted systematic performance measurements. Flight test engineer Oberleutnant Wilhelm Hoffmann supervised instrumentation installation that would document the Hellcat's capabilities with scientific precision. Accelerometers measured G-forces during friend combat maneuvers. Airspeed calibration equipment verified indicated versus true velocity. Engine instrumentation monitored manifold pressure, cylinder head temperatures, and fuel consumption across the operational envelope. The data would either confirm or refute initial impressions formed during Lerche's evaluation flight. September 23 brought detailed roll rate measurements conducted at Lair's airfield, where longer runways accommodated high-speed test profiles. Lerche flew the Hellcat through standardized sequences, while ground-based cameras recorded wing positions against timed intervals. The results arrived in Hoffmann's office the following morning, typed on forms that quantified what flight testing had already revealed. At 250 miles per hour indicated airspeed, the F6F achieved a roll rate of approximately 90 degrees per second. The Focke-Wulf 190A5 averaged 85 degrees per second at identical speed. The American naval fighter, weighing nearly twice the German interceptor's mass, rolled faster. Hoffmann reviewed the numbers repeatedly, checking calculations that seemed to contradict fundamental principles. Roll rate typically decreased with increased wing loading and higher aircraft mass. The Hellcat carried a wing loading of 35 pounds per square foot compared to Focke-Wulf's 42. Yet that advantage alone couldn't explain the performance. The answer lay in aileron design philosophy. American engineers dedicated nearly the entire wing span to aileron surface area. The control surfaces measured 8 feet in length per wing, generating control moments that overwhelmed inertial resistance. Focke-Wulf designers had optimized their ailerons for high-speed performance, sacrificing low-speed authority for reduced drag. The approaches reflected different combat doctrines and different assumptions about fighter employment. Engine testing revealed capabilities that explained American confidence in their power plants. The Pratt & Whitney R2800 produced rated power continuously for hours, without overheating or mechanical distress. German engines achieved comparable output only through emergency boost settings limited to minutes of operation. The Americans built reliability into fundamental design, accepting weight penalties for longevity. Fuel consumption measurements demonstrated another advantage. The Hellcat burned 110 gallons per hour at normal cruise power. The Messerschmitt consumed 90 gallons per hour. Yet the American fighter carried more than double the internal fuel capacity. Combat radius calculations showed the Hellcat operating 600 nautical miles from the carrier, conducting combat operations and returning with reserve fuel. German fighters defending Reich territory operated within 300 nautical miles of base. Armament analysis documented philosophical differences in weapons integration. The 650 caliber Browning machine guns harmonized at 400 meters, creating a cone of fire approximately 2 meters in diameter. The rate of fire totaled 4,800 rounds per minute combined. A 2-second burst delivered 160 rounds on target. The volume compensated for individual projectile effects less devastating than German cannon shells. American pilots trained to pour fire into targets until destruction was certain. German pilots trained for precise cannon shots that conserved limited ammunition. Both approaches achieved results, but American doctrine suited lower-skill pilots who comprised the majority of naval aviators. Structural testing revealed construction methods that explained the Hellcat's reputation for absorbing battle damage. Removing wing panels exposed internal structure featuring redundant load paths. If one spar failed, the adjacent structure carried loads until the pilot returned to the carrier. Fuel tanks incorporated self-sealing materials that swelled when punctured, preventing catastrophic fuel loss. The weight penalty approached 200 pounds. German fighters eliminated such features to reduce mass. American fighters accepted weight to reduce pilot casualties. The philosophical difference reflected resource availability and cultural attitudes toward human life's value. October brought comparison flights against Luftwaffe fighters stationed at Rechlin for evaluation purposes. Oberst Edgar Peterson, commander of the test facility, authorized mock combat exercises that would document tactical capabilities under conditions approximating actual engagement. Major Heinz Baer, an experienced fighter pilot with over 200 victories, flew a Messerschmitt Bf 109 G6 against Luftwaffe in the captured Hellcat. The exercise parameters specified initial separation of 1 kilometer at equal altitude, followed by unrestricted maneuvering until one pilot achieved firing position. The first engagement began at 4,000 meters altitude, with both aircraft approaching head-on at cruise speed. Baer initiated combat by pulling into a climbing turn to port, attempting to use the Messerschmitt's superior climb rate to gain altitude advantage. Luftwaffe followed in the Hellcat, accepting slower climb capability while maintaining energy through shallower climb angle. The Messerschmitt reached 5,000 meters first, Baer rolling inverted to locate his opponent. Luftwaffe had maintained forward speed rather than matching the vertical climb, positioning the Hellcat offset from Baer's flight path. The American fighter's energy retention in horizontal maneuvering compensated for the vertical performance deficit. Baer dove toward the Hellcat, building speed for a slashing attack. Luftwaffe rolled hard to starboard, using superior roll rate to reverse direction before the Messerschmitt could track the turn. The maneuver demonstrated the Hellcat's primary advantage in angles combat, where German fighters required coordinated aileron and rudder inputs to change direction quickly. The American fighter snapped into rolls that repositioned the aircraft faster than opponents could follow. Baer overshot, his heavier control forces at high speed preventing the rapid roll reversal needed to maintain tracking. The exercise continued for 12 minutes until Hoffmann transmitted a termination signal from ground control. Neither pilot had achieved a definitive firing solution, but the Hellcat's roll performance had prevented the Messerschmitt from exploiting its climb and speed advantages. Debriefing revealed Baer's assessment with characteristic Luftwaffe directness. The American fighter rolls like nothing I have encountered. Every time I achieved position for attack, the pilot reversed direction before I could bring guns to bear. In sustained turning engagement, the Messerschmitt maintains advantage through better climb rate, but the Hellcat pilot who understands his aircraft's capabilities can negate that advantage through aggressive rolling maneuvers. The observation confirmed tactical doctrine that American naval aviators already practiced in Pacific combat, use roll performance to avoid disadvantageous engagements, deny enemy pilots stable firing positions, force opponents into energy-depleting maneuvering. The second evaluation flight pitted the Hellcat against a Focke-Wulf 190A, 8 flown by Hauptmann Walther Dahl, another experienced pilot with over 100 victories. The exercise began identically, but Dahl employed different tactics reflecting the Focke-Wulf's strengths. Rather than attempting vertical maneuvering, he focused on slashing attacks using speed advantage and dive performance. The Hellcat's roll rate again proved decisive in defensive situations. Each time Dahl achieved an attacking position, Luftwaffe rolled away from the attack axis, forcing the Focke-Wulf to reposition before firing. The German fighter's roll rate, superior to most Allied aircraft, nevertheless couldn't match the Hellcat's control authority at combat speeds. Dahl noted after landing that the engagement felt like fighting a heavier, less maneuverable opponent who possessed one decisive advantage. The roll rate dominates tactical options. I could not maintain pursuit long enough to achieve a firing solution. Every attack ended with target aircraft rolling away faster than I could follow. The assessment validated what Pacific combat statistics already demonstrated. The Hellcat's design optimization for one specific performance parameter roll rate provided sufficient tactical advantage to compensate for deficiencies in other areas. American engineers had identified the critical capability for their operational requirements and engineered their fighter accordingly. Gunnery range testing documented another advantage that statistics suggested but flight testing confirmed. The stable gun platform characteristics allowed accurate fire during maneuvering that would disrupt aim in lighter fighters. Luftwaffe flew the Hellcat through standardized gunnery runs against towed target sleeves. The heavy airframe absorbed firing recoil without significant disturbance. The pilot maintained sight picture throughout burst duration. Hit percentage averaged 60% in deflection shots at 300 meters range. Comparable tests with Messerschmitt and Focke-Wulf produced 40 to 50% hit rates depending on pilot skill. The American philosophy of volume fire from stable platform proved effective in practice. 6 machine guns pouring rounds toward target created hit probability that compensated for individual projectile effects. German cannon achieved superior damage per hit but demanded precise marksmanship. American machine guns tolerated aiming errors through statistical probability. For average pilots with limited training time, the doctrinal difference favored American approach. Luftwaffe aces with hundreds of combat hours preferred cannon's efficiency. But wars are won by average pilots, not exceptional ones. November brought analysis of maintenance requirements and operational sustainability. Recklin's ground crews documented procedures required to service the captured Hellcat. Engine maintenance followed straightforward protocols, requiring basic mechanical skills. No specialized tools, no exotic procedures demanding factory-trained technicians. The Americans designed their fighters for maintenance by enlisted personnel aboard carriers lacking extensive workshop facilities. German fighters demanded skilled mechanics with specialized training. When those personnel became casualties, maintenance quality deteriorated. American fighters tolerated mediocre maintenance through design margins that absorbed imperfect service. The Pratt & Whitney engine required oil changes every 50 hours and spark plug inspection every 25 hours. Major maintenance intervals stretched to 200 hours before significant disassembly. The BMW 801 powering Focke-Wulf required more frequent service, more careful attention to specifications, more opportunity for maintenance errors to cause failures. American engines accepted abuse that would destroy German power plants. The reliability came at cost, measured in weight and complexity, but operational availability favored the American approach. A fighter that flies reliably proves more valuable than faster fighter that spends half its time grounded for maintenance. Fuel quality analysis revealed another disparity. The Hellcat burned fuel meeting American military specification of 100 octane rating. German fighters operated on fuel averaging 95 octane when supply permitted, often receiving lower quality that required reduced power settings to prevent detonation. The Americans possessed refining capacity to produce high-quality fuel in unlimited quantities. Germany struggled to maintain adequate fuel supplies of any quality. Industrial capacity again determined capability, beyond individual aircraft design. A superior fighter proves worthless when fuel shortages prevent operations. December brought final evaluation flights as winter weather limited test opportunities. Lersch flew the Hellcat through low-altitude performance measurements that documented capabilities below 3,000 meters. The American fighter maintained advantages in roll rate and acceleration throughout the altitude band, where combat occurred most frequently on the Western Front. German fighters optimized for high-altitude performance, sacrificed low-altitude capability. American naval fighters operated primarily at medium and low altitudes, where carrier operations dictated engagement parameters. The design priorities reflected operational requirements fundamentally different between European air war and Pacific naval campaign. Hoffmann compiled the final technical report during January 1945 as Allied armies advanced toward German borders from east and west. The document synthesized 4 months of systematic evaluation into conclusions that documented American industrial aviation capability. The Grumman F6F Hellcat represented a mature fighter design optimized for specific operational requirements. Naval carrier operations demanded reliability over peak performance. Average pilot capabilities required forgiving handling rather than ultimate agility. Long-range missions needed fuel capacity and engine reliability. The American fighter delivered all requirements through straightforward engineering that sacrificed theoretical efficiency for practical effectiveness. The roll rate performance remained the evaluation's most striking finding. Through aggressive application of aileron surface area, American designers achieved control authority that allowed heavy fighter to outroll lighter opponents. The solution violated German engineering principles, emphasizing weight minimization and aerodynamic efficiency. Yet, the solution worked. In combat, working, solutions defeat elegant theories. The Hellcat's success validated American industrial philosophy that abundant resources permitted brute force solutions to engineering challenges. Hoffmann's report noted with clinical precision, The captured aircraft demonstrates performance characteristics that confirm American capacity to produce effective weapons systems through industrial methods, emphasizing reliability and quantity over individual excellence. The F6F achieves operational success not through superior design, but through adequate design produced in overwhelming numbers. The assessment contained implications extending beyond technical specifications. American industrial capacity could sustain production rates that replaced combat losses while expanding operational inventory. German production struggled to maintain existing force levels against attrition exceeding replacement capacity. Mathematics favored the side that could afford adequate weapons in unlimited quantity over the side producing superior weapons in limited numbers. Lersch's final notation in his test logbook recorded the essential conclusion with characteristic brevity. Capable aircraft, reflecting industrial philosophy Germany cannot match. Adequate performance in all categories. Superior roll rate at combat speeds. Excellent reliability and pilot protection. Combat effectiveness achieved through systematic engineering rather than brilliant innovation. The captured Hellcat remained at Rechlin through winter months, serving as an evaluation platform for various test programs. Allied bombing raids increased in frequency and intensity as 1945 progressed. The Luftwaffe's testing facility became a target of opportunity for Allied air forces seeking to disrupt German aviation development. April 10th brought massive raid by American B-17 seconds and B-24 seconds, specifically targeting Rechlin's airfields and facilities. 170 bombers dropped high explosive across the testing grounds, destroying hangars, workshop buildings, and aircraft caught on the ground. Bureau No. 4, 1834, painted in German markings, sat on hardstand when bombs fell. The fighter that had demonstrated American industrial capability was destroyed by weapons representing that same industrial might. Lerche evacuated to Oberpfaffenhofen near Munich as Soviet forces approached from the east. His final operational flight as Luftwaffe test pilot came April 23rd, flying a Dornier Do 335 fighter in the final days before German collapse. The Hellcat evaluation joined thousands of technical reports in archives that would be captured by advancing Allied forces. American intelligence officers would review German assessments of their own aircraft, finding validation for design decisions that combat experience had already confirmed. The war ended before German engineering could apply lessons learned from studying captured American fighters. Post-war analysis of Rechlin documents revealed how thoroughly German test pilots had documented Allied aviation capabilities. Hans-Werner Lersche's flight reports on captured aircraft provided detailed technical intelligence that demonstrated professional respect for enemy capabilities. The Hellcat evaluation stood among dozens of assessments covering Spitfires, Mustangs, Thunderbolts, Lancasters, and Flying Fortresses. Each report documented capable aircraft reflecting industrial capacity Germany could not match. The cumulative evidence proved what strategic analysts already knew. Industrial warfare favored nations whose factories outproduced opponents regardless of individual weapon quality. The specific lesson regarding roll rate performance influenced post-war fighter development across multiple nations. American designers continued emphasizing control authority through generous aileron surface area in subsequent fighters. The F6F Bearcat that replaced the Hellcat featured even more aggressive roll performance while reducing overall weight. Soviet designers studying captured German reports adopted a similar philosophy in developing fighters for the Korean War. The principle remained constant. Achieving decisive advantage in single performance parameters compensated for mediocrity in other categories. Engineers could optimize for specific capabilities if they correctly identified the critical requirement. Lerche survived the war and emigrated to the United States, working for aerospace companies that valued his test pilot experience. He authored memoirs documenting his wartime career flying over 120 different aircraft types. The Hellcat evaluation received brief mention among dozens of captured aircraft he tested. Yet that particular assessment captured the essential dynamic of World War II's industrial warfare. Germany produced technically sophisticated weapons that demanded exceptional operators and comprehensive support infrastructure. America produced adequately capable weapons that average personnel could operate reliably with limited support. When attrition consumed trained personnel faster than training could replace them, the American approach proved superior. The F6F Hellcat continued service with the U.S. Navy through the war's end, achieving final victory statistics that validated its design. 5,163 enemy aircraft destroyed, 19-to-1 kill ratio maintained throughout combat operations. The aircraft enabled ordinary pilots to achieve extraordinary results through systematic design that forgave errors and amplified strengths. Post-war, the Hellcat rapidly transitioned to reserve squadrons as jet aircraft entered service. Yet its legacy influenced naval aviation development for decades. The principle that reliable, adequate performance from forgiving aircraft enabled by industrial capacity proved more valuable than brilliant performance from demanding aircraft produced in limited numbers. The Fantalist A team of the WWII's hypothetical question of what Luftwaffe pilots would have concluded after testing a captured Hellcat produces answers rooted in documented German assessments of other captured Allied aircraft. They would have recognized capable design reflecting industrial philosophy fundamentally different from the German approach. They would have documented specific performance advantages, particularly roll rate, that provided tactical benefits in combat. They would have noted the reliability and maintainability that enabled sustained operations. And they would have understood that American industrial capacity rendered individual aircraft superiority irrelevant when production volumes overwhelmed tactical advantages through strategic abundance. The Hellcat story represents a broader narrative of World War II's industrial dimension. Technical sophistication could not overcome resource disparities when industrial output determined force availability. German fighters achieved performance peaks that Allied aircraft struggled to match in specific categories. Yet Allied fighters achieved adequate performance across broader operational envelopes while maintaining reliability that kept them flying. The mathematics favored adequate performance in overwhelming numbers over superior performance in inadequate quantities. That lesson shaped post-war military procurement philosophy across Western nations. Sophisticated weapons prove valuable only when industrial capacity sustains production and operational tempo. Modern analysis of World War II aviation often focuses on specifications comparing maximum speed, climb rate, ceiling, and armament. The numbers reveal only a partial story. Operational effectiveness, derived from reliability, maintainability, production volume, pilot training quality, tactical doctrine, and industrial support capacity. The Hellcat excelled not through dominating any single specification, but through achieving adequate capability in all categories, while optimizing to role performance that provided tactical advantage in the specific combat environment where it operated. American designers identified critical requirements and engineered solutions that worked within constraints of carrier operations and average pilot capabilities. The captured Hellcat at Rechlin would have demonstrated these principles to German test pilots who already recognized patterns repeated across all captured American aircraft: strong construction, reliable power plants, redundant systems, generous fuel capacity, excellent pilot protection, straightforward maintenance, production quality, suggesting unlimited manufacturing resources. Every characteristic reflected industrial capacity that Germany could not match, while fighting multi-front war against opponents whose combined resources exceeded Axis powers by overwhelming margins. The technical evaluation would have confirmed what strategic reality already dictated. Germany faced opponents whose industrial philosophy and resource availability ensured defeat regardless of tactical innovations or individual weapon superiority. The evening of May 2nd, 1945, Soviet forces occupied Rechlin's ruins. The testing facility that had evaluated Germany's most advanced aviation technology lay shattered by bombing and deliberate demolition. Scattered wreckage included remains of aircraft from dozen nations, all reduced to scrap metal, valuable only for reconstruction efforts. The captured Hellcat that briefly wore Luftwaffe markings had been destroyed weeks earlier by weapons representing the industrial power that created it. The cycle completed itself with appropriate symmetry. American industrial capacity built the fighter, German technical expertise evaluated it, and American industrial capacity destroyed it. The outcome illustrated the immutable principle of industrial warfare: Adequate weapons produced in overwhelming numbers defeat superior weapons produced in inadequate quantities when attrition consumes forces faster than industry replaces them. The legacy of the Hellcat extended beyond statistics and specifications into philosophical understanding about weapon system design. The F6F proved that systematic engineering focused on operator needs and operational requirements produced more effective results than pursuing theoretical performance peaks. American designers built fighters for average pilots operating from challenging environments with limited support. German designers built fighters for exceptional pilots operating from established bases with comprehensive maintenance. Both approaches succeeded within their contexts. But World War II's attrition rates ensured average pilots outnumbered exceptional pilots, while Allied bombing degraded German infrastructure supporting sophisticated aircraft. The American approach proved scalable and sustainable. The German approach proved vulnerable to attrition and resource constraints. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.